Module F, simultaneous confidence intervals. We have 2 modules to go, and we have one very important multiplicity topic to cover in this module. As you may remember, back in Module C, we defined 3 ways of summarizing inferences in multiplicity problems, or another way to put it, 3 ways to presenting multiplicity adjustments. We can first of all compute adjusted significance levels, or adjusted p-values, or finally adjusted confidence limits that are also known as simultaneous confidence limits. In modules C, D, and E, we focused on adjusted p-values because this is how multiplicity adjustments are typically presented in publications, in clinical study reports. But simultaneous confidence intervals play an important role because they help us estimate the magnitude of the treatment effect after an appropriate multiplicity adjustment, and this is very useful in the context of risk-benefit assessments in clinical trials. There's only one section in this module. This is section F1. We're going to begin with a general discussion of the role of confidence intervals. This includes univariate confidence intervals, and I will then introduce simultaneous confidence intervals, which means confidence intervals that are adjusted for multiplicity, and I will show you how to construct simultaneous confidence limits for some multiple testing procedures. The key word in this sentence is some. As you will learn in a few minutes, simultaneous confidence intervals are quite easy to derive for basic single-step procedures, and we talked about those in Module C. But when we enter the world of more powerful multiple testing procedures, and by that I mean stepwise procedures, it turns out that the process of constructing simultaneous confidence intervals becomes a lot more challenging, and the results, to be honest with you, are not completely satisfactory. The importance of reporting multiplicity adjusted or simultaneous confidence intervals for key parameters in clinical trials, such as the mean treatment difference, when we're dealing with a continuous outcome variable. The importance of this aspect of multiplicity adjustments is highlighted, as you see on the slide, in the EMA guidance document. Specifically in section 10.2, you will find the following statement. As can occur with multiple testing, multiple confidence intervals may also increase the chance of false decisions, since the probability that a set of multiple non-adjusted confidence intervals cover correctly all parameters to be estimated would usually be less than the pre-specified nominal coverage probability related to each single confidence interval. And that's why this is the topic that will be discussed in detail in this module. Section F1, simultaneous confidence intervals. We're going to begin with the basics. We will step back to discuss univariate confidence intervals first. Those intervals are commonly used in univariate testing problems to help us estimate the magnitude of treatment differences. And as you know, a univariate confidence interval guarantees that the true value of the single parameter of interest, for example, the mean treatment difference, lies between the lower and upper limits with a pre-specified probability. Most commonly, this coverage probability is set to 95%. And so we can make a statement that the treatment effect is significant, and that happens when we reject the null hypothesis of interest. And in addition to that, we can present a confidence interval which gives us the likely set of values for the mean difference between, for example, the experimental treatment and control. And simultaneous confidence intervals are a natural extension of standard univariate confidence intervals, and they're used in problems where there are several parameters of interest. For example, we may be interested in estimating the mean effects at multiple dose levels in a clinical study with several dose placebo comparisons. So simultaneous confidence intervals are used in multiple testing problems to define a multivariate region as opposed to a univariate region that is supposed to cover the multivariate true parameter with a pre-specified probability, and the overall coverage probability is typically set again at 95%. And there has been increasing emphasis on the use of simultaneous confidence intervals in clinical trials because they facilitate, as I said a minute ago, risk-benefit assessments, and they enable the trial sponsor and also regulatory reviewers to understand the balance between the magnitude of a beneficial effect and other clinically important indicators or considerations, for example, indicators related to safety variables. To define univariate confidence intervals and then simultaneous or multiplicity adjusted confidence intervals, we will of course need to introduce some notation, the parameters of interest. So on top of a standard multiplicity testing problem that we have defined in this course, we need to define a parameter estimation problem. We consider here, for the sake of example, a clinical trial with M null hypotheses that are defined in terms of the M parameters defined on this slide. Those parameters are denoted by theta 1 through theta m, and these are the parameters of interest. As I said before, this is probably the mean difference when we analyze continuous endpoints, or the difference in proportions when the primary endpoint in a clinical trial is binary. And finally, in clinical trials with time to event endpoints, the parameter of interest is most likely the log hazard ratio. In addition to that, we will use the standard hat notation. Theta I hat is going to be the parameter estimate, which will be assumed to be normal. It will be centered around the true value of the underlying parameter, which is theta I, and the variance will be sigma I squared. And finally, SI is going to denote the sample standard error for this estimate, theta I hat. And the null hypothesis of interest here will be formulated, of course, in terms of the parameter theta I. We're going to assume that under the null hypothesis, this parameter theta I is less than or equal to 0. And here, as before, I would like to emphasize that we're focusing on a one-sided testing problem, and therefore we are defining a one-sided type 1 error rate, which is denoted by alpha. Let us begin with a basic case of a univariate confidence interval for each of the parameters that we defined on slide 7. We will just use this opportunity to refresh our memory. Since the parameter estimates on slide 7 were assumed to follow a normal distribution, or in certain cases we can only assume asymptotic normality, then a one-sided confidence interval for theta I is going to be given by Li. It will be the lower limit, the upper limit is going to be infinity, and Li, as you can see on the slide, is simply given by the estimate of the parameter of interest, which is theta I hat, minus the appropriate quantile of the standard normal distribution, denoted by Z alpha, times the sample standard error of this particular estimate. And as you can see, we're defining only a lower limit on the slide, and this is done for two reasons. First of all, this formulation of confidence intervals is consistent with the one-sided hypothesis testing problem, and I emphasized at the very beginning that throughout this course we're going to focus on one-sided hypothesis testing problems, and of course it's very easy to extend one-sided confidence intervals to two-sided confidence intervals, but here, to save space and time, we will just deal with the one-sided formulation of this problem. And therefore, we're going to focus only on the lower confidence limits that are again denoted by Li, and we'll never explicitly specify the upper limit of those one-sided confidence intervals, because the upper limit is going to be equal to plus infinity. And the coverage probability of this univariate one-sided confidence interval is, we can see here, is equal to 1 minus alpha. For example, if alpha is equal to 0.025, then the coverage probability is guaranteed not to be lower than 97.5%. So this univariate confidence interval works well in a univariate estimation problem, but the overall coverage probability for all m parameters in this multiplicity problem, of course, is not going to be controlled. If we use a univariate or unadjusted confidence interval for each individual parameter, then the overall coverage probability can be shown to be less than 1 minus alpha, for example, less than 95%, because roughly speaking, the univariate confidence intervals are too narrow. They need to be adjusted, they need to be corrected for multiplicity to guarantee a predefined overall coverage probability. And this is exactly what we're discussing on slide 9. One-sided simultaneous confidence intervals for the thetas are defined to guarantee that the overall coverage probability is at least 1 minus alpha, and we're going to denote the lower limits of those one-sided simultaneous confidence intervals by Li tilde. And the formula shown on the slide presents a mathematical formulation of the verbal statement that I just made a second ago. It shows that the probability of covering the true values of the thetas, we have m parameters here of all those theta, is not going to be less than 1 minus alpha. And an additional very important property of simultaneous confidence intervals is consistency. They must be consistent with the associated multiple testing procedure. And this property is, of course, very similar to the consistency property in the univariate case. If we define a one-sided confidence limit for a single parameter, for example, theta I, then the lower confidence limit, denoted by Li tilde, must be greater or equal to 0 if the null hypothesis based on this parameter is rejected. And this null hypothesis is, of course, denoted by Hi. And in the multivariate case, it's exactly the same rule. The lower confidence limit must be greater than or equal to 0 if the null hypothesis is rejected. Now that we have defined simultaneous confidence intervals in general multiplicity problems, let us talk briefly about the challenges that we face when we set up simultaneous confidence intervals for popular multiple testing procedures. Very briefly, and this is the main challenge here, there is no standard, there's no automatic way of extending univariate confidence intervals to multivariate or simultaneous confidence intervals. When it comes to, say, adjusted p-values, they can be computed for any multiple testing procedure. There's a universal algorithm that needs to be applied to derive a multiplicity adjusted p-value for each individual hypothesis for any multiple testing procedure. But if you're interested in computing simultaneous confidence intervals for a given multiple testing procedure, there is no standard approach that would be applicable to all procedures. But the good news here is that for the class of basic single-step procedures, simultaneous confidence intervals are quite easy to set up. And this includes, of course, the Bonferroni and Dunnett procedures that we introduced in modules C and E. And the underlying algorithm is very straightforward. Many SAS procedures, for example, support simultaneous confidence intervals for those two procedures. But as we know, the main problem with single-step procedures is that they're not very powerful. And for this reason, one of the main take-home messages from this entire online training course is that we ought to focus on stepwise procedures, based specifically on the closure principle, because we know that they offer a uniform power advantage over basic single-step procedures, and for this reason they are recommended for all clinical trial applications. But the bad news for stepwise procedures is that, first of all, constructing simultaneous confidence intervals for stepwise procedures is generally a challenging task, and sometimes it's not even known how to set up those simultaneous confidence intervals. And secondly, and that may be even more discouraging, simultaneous confidence intervals for powerful procedures are not always meaningful. We can say in general that the more powerful a multiple testing procedure is, then the less meaningful, the less informative the associated simultaneous confidence intervals are. This is indeed very unfortunate that with more efficient multiple testing procedures, we lose the ability to construct meaningful simultaneous confidence intervals, and this important property of stepwise procedures is referred to in the FDA guidance on multiple endpoints. Section 4 of this document provides some background information on single-step and stepwise procedures, and it states the following. Statistical methods for addressing multiplicity issues are broadly classified into two types: single-step and multi-step procedures. Single-step procedures provide for parallel or simultaneous testing and simultaneous adjusted confidence intervals for assessing the magnitude of the treatment effects. Single-step procedures tend to cause loss of study power, so that sample sizes need to be increased in comparison to sample sizes needed for a single endpoint study. And the most important point, as we see on the slide, multi-step procedures, which means stepwise procedures, are generally more efficient in that they better preserve the power of the tests, but they do not readily provide adjusted confidence intervals. In those cases when we can define a set of simultaneous confidence intervals associated with a stepwise procedure, here's the main difference between the algorithms used by single-step and more efficient stepwise procedures. In the single-step case, null hypotheses are tested independently of each other, as we've said many times before, and this means that they can be tested in any order. And as a direct consequence of that, simultaneous confidence intervals are defined independently for each individual parameter theta I. And this explains why simultaneous confidence intervals are so easy to define for single-step procedures such as the Bonferroni or single-step Dunnett. However, and by contrast, in the stepwise case, if we select, for example, step-down procedures, as shown on the slide, null hypotheses are tested sequentially, beginning with the hypothesis that corresponds to the most significant p-value, as you remember, and the outcome for a null hypothesis depends on the rejections or acceptance of the hypotheses that were placed earlier in the sequence, and as a result of that, the simultaneous confidence intervals for the individual parameters are not independent anymore. They are interdependent, and the simultaneous confidence intervals need to be computed using this two-stage algorithm. The first step would be to test the null hypothesis in a given multiplicity problem and define the set of rejected hypotheses. And then secondly, using this set of rejected hypotheses, we define the simultaneous confidence intervals for the individual parameters theta I. With this general approach in mind, let's briefly talk about simultaneous confidence intervals for nonparametric single-step procedures and stepwise procedures, as well as semi-parametric stepwise procedures. And then in the second half of this module, we will discuss parametric procedures. So, beginning with a general class of two-stage algorithms for setting up simultaneous confidence intervals, this general approach was developed for non-parametric stepwise procedures. It's a powerful general approach which can be used to derive simultaneous confidence intervals for multiple non-parametric procedures such as the Holm, fallback, and chain procedures. And the papers that dealt with this topic, as you see on the slide, were published from 2008 to 2009. And more recently, in 2011 and 2012, there were additional publications that expanded this general approach to semi-parametric stepwise procedures such as the Hommel and Hogberg procedures. But we're not going to talk about those stepwise semi-parametric procedures in this module because unfortunately they are not very meaningful from a practical perspective. It will be sufficient to go over the process of setting up simultaneous confidence intervals for stepwise procedures that are non-parametric or fully parametric, and our general conclusions are going to extend directly to the class of semi-parametric procedures as well. So we're going to begin with non-parametric multiple testing procedures. The most basic non-parametric procedure is of course the Bonferroni procedure. It's a very simple single-step procedure, and the lower limits of one-sided simultaneous confidence intervals for the individual parameters based on this procedure are defined simply by adjusting the alpha level in the quantile of the standard normal distribution. So the formula that we see on the slide is a direct extension of a formula that we defined a few slides back, and that formula defined the lower limit of a one-sided univariate confidence interval. And the only difference that we can see here is that instead of using alpha to compute the quantile of the standard normal distribution, we divide that alpha by m. It's obviously very straightforward, as you can see. And this slide shows the algorithm used for defining lower limits of one-sided simultaneous confidence intervals for the individual parameters in an estimation problem when multiplicity is adjusted using the Holm procedure. This is actually the second step of this two-step algorithm. The first step, if you remember, started with simply applying the Holm procedure and defining a set of rejected hypotheses. And then, depending on how many hypotheses are rejected, there are three possible cases. Case 1, in this first case, the Holm procedure rejects some hypothesis and accepts some hypothesis. And in this case, the lower confidence limit for any rejected hypothesis, once again denoted by Li tilde, is simply set to 0. This is clearly not very informative, since this essentially tells us that the one-sided simultaneous confidence interval for this parameter extends from 0 to infinity. In the second case, we assume that all null hypotheses in this multiplicity problem are rejected, including the current hypothesis denoted by Hi, in which case the lower confidence limit for theta I is defined as the larger of 0 and this formula, and this formula essentially defines the lower limit for the Bonferroni procedure. And finally, in case number 3, we assume that the current hypothesis Hi is accepted, and other null hypotheses may be accepted or they may not be, may be rejected or may not be rejected. And in this case, the lower confidence limit is simply the Bonferroni based lower confidence limit, but it's based on M minus R hypothesis, where R is the number of rejected hypotheses in this problem. And as a result, the more null hypotheses are rejected, then the less conservative this lower confidence limit becomes. When we look at the properties of the resulting simultaneous confidence limits, we see that the lower confidence limit for a parameter is set to 0 if the whole procedure rejects the corresponding null hypothesis of no treatment effect, and the only exception is when the procedure rejects all hypotheses. In this particular case, the lower limit may be greater than 0, but sometimes it may be equal to 0. So in most cases, lower confidence limits for rejected null hypotheses are not very informative. Most of the time they're simply set to 0. And I alluded to this general fact earlier in this module when I said that the second challenge we face when we construct simultaneous confidence intervals for stepwise procedures is that those confidence intervals are not always meaningful, they're not informative, they don't really help us find the region of likely values for the parameters of interest, for example, the mean treatment differences in a clinical trial. On slide 17, we're going to illustrate the algorithms for computing one-sided simultaneous confidence intervals for the Biopharmaceutical procedure, which is once again a single-step procedure, as well as the Holm procedure, which is a more efficient stepwise procedure. And we will do this using example 4 based on the type 2 diabetes trial. We've used similar summaries of results before. This particular set of one-sided p-values was labeled scenario 5 earlier in this online course. This table shows us the one-sided p-values for each individual dose placebo test. It also shows the parameters of interest, and those are the mean dose placebo differences that are shown in the central column in this table. And to remind you, the primary endpoint in this type 2 diabetes trial is the change from baseline to week 24 in hemoglobin A1C, and it is expressed in percentage points. And the values that you see in this table are the mean differences between each dose and placebo based on this endpoint, and a larger value of this mean treatment difference indicates a beneficial treatment effect. And there are other useful parameters that may help us are shown below the table. We assume a balanced design and the sample size per group is 90 patients. We define the pooled standard deviation. And finally, it's helpful for us to define the ordered hypothesis. It's obviously a very important consideration in the context of step-down procedures, such as the Holm procedure. Using the p-values that were defined in the table on slide 17, we need to first find the set of rejected null hypotheses. In this case, as before, we see the ordered hypothesis on the horizontal axis, and the orange dots represent the one-sided p-values for each individual dose placebo comparison. And this step, of course, is not required for the Biopharmaceutical procedure. It's a single-step procedure. And so the algorithm for computing one-sided simultaneous confidence intervals for the 3 mean dose placebo differences is very straightforward. But for the stepwise Holm procedure, this step is critical, and we can easily verify that the first hypothesis in the sequence is going to be rejected because the corresponding p-value is less than alpha over 3. That enables us to continue to the next hypothesis in the sequence, and that p-value is less than alpha over 2, which implies that the Holm rejects that hypothesis. The last hypothesis in the sequence on the very right of this plot, the p-value associated with that hypothesis is above the alpha threshold, and therefore the Holm cannot reject that last hypothesis in the data-driven sequence. The conclusion, presented at the bottom of the slide is that only the hypotheses H1 and H3 are rejected by the Holm procedure. Using this information, we can now define the simultaneous confidence intervals for the Bonferroni and Holm procedures. And the left-hand plot on the slide shows the lower confidence limits for the Bonferroni procedure with a one-sided alpha of 0.025, which means immediately that the overall coverage probability for those three confidence intervals is going to be 1 minus alpha, or in other words, it's 97.5%. The limits that are represented by the orange dots in the left-hand plot are consistent with the decision rules that we presented on slide 18. We remember from that slide that the Bonferroni procedure rejected only one hypothesis. That was the very first ordered hypothesis. And as a result, we can see from the left-hand plot that the lower limit for that hypothesis is non-negative, but the lower limits for the other two hypotheses are below the dotted line that represents 0. They are in the null zone, and that means that those confidence intervals include 0. There is simply not enough evidence to reject these hypotheses. Now, the right-hand plot displays the lower confidence limits based on the Holm adjustment. They are specifically derived based on the two-step algorithm that we defined a few slides back, and it utilizes the information from slide 18. It utilizes information on the number of hypotheses rejected by this particular procedure. And if you remember from that slide 18, the Holm procedure rejected the first ordered and the second ordered hypothesis. And the lower limits for those two hypotheses are non-negative. Well, they are set to 0 actually, but they're non-negative. And therefore, from a formal perspective, the decision rules and lower confidence limits are consistent. But once again, those lower confidence limits are not informative. They're both equal to 0. And for the last hypothesis in the data-driven sequence, there's a little bit of good news, because both procedures, the Bonferroni and the Holm, rejected the third-ordered null hypothesis. And we can see here a slight advantage of using the more powerful Holm procedure. The lower limit for that last hypothesis is sharper, which means that it's closer to 0 for the Holm procedure compared to the Bonferroni procedure. And in fact, this lower limit in the right-hand plot for the, once again, for the third order hypothesis is so close to 0 that it looks like it's actually equal to 0, but in reality it is a negative value. The results that we have discussed, specifically the fact that simultaneous confidence intervals for more efficient stepwise procedures such as the Holm procedure are interesting from a theoretical perspective. This was a fairly challenging task to derive those simultaneous confidence intervals, but it is very helpful to look at the big picture and understand how those simultaneous confidence intervals could be used in the context of real clinical trial applications. And this challenging situation is described in the EMA guidance in section 10.2, as you see on the slide. Informative confidence regions that correspond to multiplicity procedures may, however, not always be available or may be difficult to derive. If the confidence regions do not correspond to the hypothesis testing procedure, different conclusions are possible. For example, a confidence interval excluding the null hypothesis combined with a non-significant testing result, or vice versa. And this quote continues on the next slide. The decision should, however, be based on the hypothesis test. In that case, it is advised to use simple but conservative confidence interval methods, such as Bonferroni corrected intervals, ensuring that the uncertainty about the beneficial effects is properly understood. What this quote refers to is that there have been attempts to construct a hypothesis testing procedure, multiplicity testing procedure, based on a more efficient multiplicity adjustment, such as the Holm procedure, but the resulting adjusted p-values would be accompanied by Bonferroni-based simultaneous confidence intervals for the parameters of interest, such as the mean treatment differences. And to be honest, those attempts have not been very successful, because if you focus on the adjusted p-values, the sponsor may conclude that the treatment effect in a certain dosing arm is significant, but then when the sponsor switches to the confidence intervals, the mean treatment difference may end up being negative, which implies that it's premature to conclude that this particular dose is effective. Well, this would be the case when the corresponding null hypothesis is rejected by the Holm, but the Bonferroni procedure fails to reject this hypothesis. For example, the second ordered hypothesis in the example that we discussed just a couple of minutes ago. So this is in fact a problem, and to be honest, it's not entirely clear how to approach this problem in practice. Looking at this quote, this recommendation from the EMA guideline on multiplicity in clinical trials, I think it may be cleaner, if you will, to present multiplicity adjusted p-values based on the most efficient multiple testing procedure. And when it comes to confidence intervals, simply present the univariate or unadjusted confidence intervals, but make it clear that these intervals are not corrected for multiplicity, and they may be inconsistent with the multiplicity adjusted p-values. Those univariate confidence intervals simply serve as a general reference point, and they should not be overinterpreted. Parametric multiple testing procedures. Earlier in this module, we introduced algorithms for computing simultaneous confidence intervals for non-parametric procedures. That included single-step and stepwise procedures such as the Bonferroni and Holm. And the same ideas can now be applied to more powerful parametric procedures. First, we need to define a parametric model that will provide a foundation, the general framework for parametric multiplicity adjustments. And this will be, as you see on the slide, a one-way ANOVA model for a clinical trial with several dose placebo comparisons. We used a similar model in Module E. In this case, Yij denotes the outcome for the jth patient in the ith group. Mu-I is the treatment effect in the ith group, and the second term in this model is the error term. The parameter of interest, theta I, is the mean treatment difference. It's mu-I minus mu0, so it's the difference between the mean effect in the ith group and the placebo group. The sample means will be denoted by theta I hat, and we're going to also use the pooled sample standard error S, because in this context it's a one-way ANOVA model. It makes more sense to pool the information across the arms to define the pooled sample standard error as opposed to looking at parameter-specific standard errors. And the final parameter that we will use in this section of the module is the number of degrees of freedom, denoted by nu, and it's a simple product of m plus 1 times n minus 1, because we here assume a balanced trial design with n patients per arm. In this parametric setting, we can define simultaneous confidence intervals for the Dunnett family of parametric procedures that we introduced in Module E. And this includes a basic parametric procedure, the single-step Dunnett, and also more powerful stepwise procedures such as the step-down Dunnett procedure. The algorithm for the single-step Dunnett is very simple, because just like in the Bonferroni case, simultaneous confidence intervals can be also constructed for the step-down Dunnett. However, I would like to point out that not much is known about other stepwise parametric procedures. for example, the step-up Dunnett procedure, or perhaps parametric versions of the fallback and chain procedures. Those simultaneous confidence intervals have not been developed yet. So the situation in the parametric case is quite similar conceptually to what we saw in the case of non-parametric procedures. Simultaneous confidence intervals for single-step procedures are easy to derive, but simultaneous confidence intervals for stepwise procedures such as the step-down Dunnett, more difficult but feasible, and simultaneous confidence intervals for more complex stepwise procedures, the answer may be unknown. Beginning with the basic single-step case, the lower limit of one-sided simultaneous confidence intervals for theta I, which is the mean treatment difference for the ith dose, is very similar to the lower limit of the univariate confidence interval. The only difference here is that, just like in the bond-forming case, the only difference is that we're going to replace the quantile of the standard normal distribution. It used to be Z alpha, and now it's replaced by D alpha. And D here is the quantile of the Dunnett distribution. It's much more relevant in the context of parametric adjustment procedures than the standard normal distribution. And this is how the Dunnett multiplicity adjustment enters the picture, and this causes the confidence interval to become wider. And I'm also going to jump a little bit ahead and remind you how we define the critical values for the step-down Dunnett procedure in Module E. They're defined using the quantiles of the Dunnett distribution with decreasing values of the first parameter. And you see the formula that is used to define those critical values, denoted by Ci, at the bottom of the slide. The more complex, but as I pointed out, still feasible case is the derivation of simultaneous confidence intervals for the step-down Dunnett procedure. It is also based on a two-step algorithm, which is very similar to the algorithm that we use to define simultaneous confidence intervals for the Holm procedure. First, as before, we apply the step-down Dunnett. We derive the set of rejected null hypotheses, and then we consider the following three mutually exclusive cases. Case number one, some hypotheses are rejected, some hypotheses are accepted, but if we assume that the current hypothesis Hi is rejected, then the lower limit of the confidence interval for theta I is automatically set to 0. Case number two, here we assume that all null hypotheses are rejected, which includes, of course, the hypothesis of interest, Hi. In this case, the lower confidence limit is the maximum between 0 and the second quantity, the second formula here, which is the Dunnett lower confidence limit. And by this I mean the basic single-step Dunnett confidence interval. And finally, case 3. If the current hypothesis is accepted, then the lower confidence limit is simply the lower confidence limit for the single-step Dunnett procedure, but it's applied to a subset of null hypotheses. It depends on the critical value, C r plus 1, and r is the number of rejected null hypotheses. It is fair at this point, just like we did in the case of the Holm procedure, is to summarize the key properties of the resulting simultaneous confidence intervals. And as you can see, everything here is a very straightforward extension of the rules that we applied to derive confidence intervals for the Holm procedure, and we extend them now to a parametric case. Shouldn't be really surprising because the Holm is a step-down non-parametric procedure, and the step-down Dunnett is a extension of the Holm to a parametric setting. The conclusions are very similar. In most cases, unfortunately, the lower confidence limits for rejected null hypotheses are simply set to 0, and as a result, they are not informative for their use in practice. We will now use the same example that we used with the Bonferroni and Holm procedures, exactly the same set of parameters, to compute the lower confidence limits for the single step and step down Dunnett procedures. And we're going to compare those limits to those that were based on the Bonferroni and Holm procedures. This slide looks very much like slide number 19 that summarizes simultaneous confidence intervals for the non-parametric procedures. And just like on slide 19, here we have two plots. We see lower confidence limits for the single step procedure and lower confidence limits for the step down procedure on the left and then on the right, respectively. The overall coverage probability is again 97.5%. It's based on the one-sided alpha of 0.025. And beginning with the single step procedure, looking at the plot on the left-hand side, a careful comparison of the Bonferroni and single step Dunnett procedures reveal that the single step Dunnett procedure produces slightly sharper, lower confidence intervals, or in other words, that are slightly more informative, which is a simple consequence of the fact that the single step Dunnett procedure uses more information. It is more powerful, after all, than the basic Bonferroni, so it gives us tighter confidence limits. And the same is also true when we compare the Holm and step down Dunnett procedures and focus on the plot shown on the right hand side. But when we compare the two plots on this slide, we see that improved power when we go from the single step to the step down procedure does not translate into more informative confidence limits. We also saw that on slide 19 when we compared and contrasted the simultaneous confidence intervals derived from the Bonferroni and Holm procedures. Since the step down procedure does not reject all null hypotheses in this type 2 diabetes trial, the lower confidence limits for the first two ordered hypotheses that it rejected, they are set to 0. And as a result, the less powerful single step procedure gives us more meaningful lower limit for the first ordered hypothesis. It is positive, and this information will help facilitate the decision-making process. Whereas in the step-down case, the lower limit is set to 0 whenever we reject a null hypothesis. Of course, it is not very helpful. Software implementation. The rest of this module covers software implementation issues. There are no standard solutions in SAS for computing simultaneous confidence intervals, and so I will present two custom macros, the pval CI macro and the par CI macro, developed by my colleagues and myself. The first macro supports the computation of simultaneous confidence intervals for certain p-value based procedures. Specifically, it supports the Bonferroni, Holm, and fixed sequence procedures. And the second macro, the par CI macro, supports simultaneous confidence intervals for the single step and step down Dunnett procedures. As far as our implementation is concerned, a useful function is included in the Mediana package. It's the adjust CIs function. It stands for adjust confidence intervals function. And it supports, as you can see here on the slide, the computation of simultaneous confidence intervals for a number of non-parametric procedures, as well as parametric procedures such as the single step and step down Dunnett procedures. Just like the SAS macros on slide 30, this function focuses on one-sided simultaneous confidence intervals that we have discussed earlier in this module. We're going to consider the following set of the test statistics and estimated parameters of interest that represent, in this case, the mean treatment differences for 3 dose placebo comparisons in example 4 in the type 2 diabetes trial, the sample size per group is going to be assumed to be 90 patients, and the pooled standard deviation is assumed to be 1.6. I will first present the computation of one-sided simultaneous confidence intervals based on non-parametric procedures in SAS. The p-val CI macro requires the following dataset. This dataset includes multiple variables, and the following variables are required. First of all, raw p is the set of raw or unadjusted p-values. EST is the set of estimated parameters of interest, for example, the mean treatment differences. SD is not actually a required parameter. It was included here mostly for the sake of convenience. The weight parameter is important. The hypotheses here are assumed to be equally weighted, and therefore the common weight is set to 1/3. The last required parameter is SE. That's the pooled standard error, which can be easily derived, as you see on the slide, from the pooled standard deviation and the common sample size of 90 patients per arm. When we pass the dataset created on slide 33 to the p-val CI macro, we also need to specify the joint coverage probability for the 3 resulting one-sided simultaneous confidence intervals for the true treatment differences in this clinical trial. The joint coverage probability is set to 97.5%, and it corresponds to one-sided alpha of 0.025. The data set created by this macro, ADJCI, this data set contains several variables corresponding to simultaneous confidence intervals for multiple non-parametric procedures, and we're going to select only the variable that corresponds to the Holm procedure. It's the Holm variable. But in addition to one-sided simultaneous confidence intervals based on the Holm procedure, this macro, as you can see, also supports simultaneous confidence intervals for the Bonferroni, fixed sequence, and fallback procedures. This is the output of the p-val CI macro in this clinical trial. We see here is the set of lower one-sided confidence limits for the univariate analysis without any multiplicity adjustment, and the column on the right hand side shows the lower limits of the adjusted or simultaneous confidence intervals based on the Holm procedure. As we said before, every time the Holm procedure rejects a null hypothesis, this lower limit is set to 0, so it is not informative, and that's why the first value is 0 and the last value is 0. However, in this particular case, the Holm procedure failed to reject the second hypothesis, and for this reason we end up with a slightly informative lower confidence limit, which is slightly below 0. It's a negative, it's a non-zero value. The PAR-CI macro needs to be invoked if we are interested in setting up one-sided simultaneous confidence intervals based on parametric procedures. The required data set is defined on the slide, and the following variables are included in this data set. T denotes the set of test statistics. EST is as before is the set of the parameters of interest, the sample values of those parameters. For example, the estimated mean treatment differences in example 4. SD is not a required parameter. It's used here again for convenience. The required parameter is SE, which denotes the common standard error. The process of computing simultaneous confidence intervals for parametric procedures is very similar to the process that I presented on slide 34 when we discussed non-parametric procedures, specifically the Holm procedure. We just need to switch to the PAR-CI macro. The macro call, as you can see, is exactly the same as before. We select, in this case, the Dunnett variable to print the one-sided simultaneous confidence intervals for the true mean treatment differences, that are based on the single-step Dunnett procedure. But in addition, I would like to point out that we could have printed the one-sided simultaneous confidence intervals based on the step-down Dunnett procedure simply by focusing on a different variable name. This variable name is shown at the bottom of the slide. This is the output of the parci macro. As before, it lists the one-sided lower confidence limits based on the univariate analysis before any multiplicity adjustment, and you also see the lower confidence limits for the single-step Dunnett procedure. Now that we have discussed available SAS tools, let's move on to R-based tools for computing simultaneous confidence intervals in clinical trials. We will rely on the adjust CI's function from the Mediana package. And to remind you, we use the adjust p-values function to compute multiplicity adjusted p-values for nonparametric, semi-parametric, and fully parametric procedures in modules C, D, and E, and to construct multiplicity adjusted, or in other words, simultaneous confidence intervals, we will need to call the adjust CI's function. This slide provides an example for computing simultaneous confidence intervals for the whole procedure. Just like the adjust p-values function, this function, adjust CI's, this function has two required parameters. It's, first of all, the vector of parameter estimates. In this particular case, it's the vector of mean treatment differences at the 3 doses. The second parameter is the multiple testing procedure. It's the whole procedure in this case. And finally, there's an optional parameter, par, that can be used to pass multiple values such as standard deviations and sample sizes to this function. And in the context of this particular implementation, we need to specify the vector of parameter-specific standard deviations. The standard deviations are all equal to 1.6 in this setting. We also need to pass the common sample size denoted by n. N is equal to 90. And the joint coverage probability, which is equal to 97.5%. The resulting set of lower confidence limits for the true treatment mean differences is shown under output. And a similar function call can be used to construct one-sided simultaneous confidence intervals based on the Bonferroni, single-step Dunnett, and step-down Dunnett procedures. We just need to specify the appropriate procedure from the list that we see at the bottom of this slide.